elements or things. One is the Turing Machine's assignment. If you're getting errors, you remember you have to click the advanced options and say what you want your start state to be. It defaults to a start state called 0. It can be whatever you want, but you have to put what you want your start state to be. Type that in the box, and it's going to default to 0 otherwise. So if you're getting that error, that's just why. Not a big deal. Two other things that I noticed, just from the ones that I've looked through, don't forget to make sure that your machine returns to the far right X when it's finished. That is kind of an arbitrary rule, if you will, but it's just a convention that we're all going to stick with. One of the reasons that that would be good is because if we wanted to combine several Turing machines, that way they're sort of compatible, if you will. So getting the thing back to the right index should be really easy. Okay, just don't forget that. And it should both start and end at the right index. Okay. For the bare bones assignment that you guys have, I really should have done it the way I did because there's the auto-graded question and then two non-auto-graded questions. I should have made it two separate assignments. So that's my bad. But all it means is that if you do another attempt, right, so you get to figure out the auto-graded part first, and then you're working on the other ones, you'll every attempt you'll have to put back in the auto-graded answer. I mean, it's just a number, right? So it should be pretty easy. But and that's yeah, I should have done it that way. I should have split it into two assignments, but sorry. And the third thing is, what does S1 and S2 mean? Huh? Just stuff, right? Think of it as just a placeholder for what would be conceivably any number of other bare bones instructions, but it's just going to be a placeholder. So your things are just going to have or your, for the third question, you'll just have some stuff, and then S1 will be aligned in one of them, and S2 will be aligned in the other. And what are those? Not important. Just think of it as it's some sequence of instructions. And other than that, I think that's it on the Canvas stuff. Well, for now, I've got a lot of stuff to post this weekend and some schedule updates and things now that I've kind of figured out how the rest of the semester is going to work. Just to plug this in your ear, and I'll remind you, of course, on Monday. Wednesday next week, we will not meet in this room. We will meet in the library in the instruction area, which is you walk in and the stairs are in front of you. It's kind of off to the right, where a bunch of computers and stuff like that are. So we'll meet over there instead of in here. And we'll be doing basically a Andrew, what's his last name? Taylor, in the library is going to do a brief introduction to three tools, one for doing audio, one for doing simple video editing, and one for doing simple web page construction, because those three media are your choices for your final projects. You're going to either do a podcast, a video, or a sort of fancy looking website page. And so he's going to give you a brief introduction to each of the three sets of tools so that you guys all kind of know, well, at least the initial basics of how to get started on something. And I'll have the actual assignment for you guys too with the parameters and whatnot, I guess Monday or Wednesday. Okay, so that's all the business for now. But just pay attention to Canvas for some updates on some other things. And we'll do our second exam Friday next week. I'm still trying to figure out exactly how we'll do it, whether I'll just do the thing with the folder again, or if I can't trust you guys, I'll come up with something else. I realize that I'm yelling at most of you don't deserve to be yelled at, but anyways, that's the breaks. Okay, so let's return to where we were at the end last time. We figured out the trick for how to flip the bits, okay, using the operations that we have in this machine language. And so what was the trick? You have a number, you want to flip all its bits. How do you do it? Not add. So we took the number of all ones. What did we do with that number? Didn't subtract either. We exclusive OR, right? Remember? Then what did we do? Add 1, right? So the procedure for getting the negative of a number is to flip the bits and add 1, right? So the flip the bits part was the one that required thought, and we realized that the trick is you, um, all you need to do is take the bit pattern that has all ones. You have your desired or your initial bit pattern and use the exclusive OR operation. So if you exclusively OR against a 1, if you are a 1, what's 1 XOR 1? 0. And what's 0 XOR 1? 1. So it flips ones to zeros and zeros to ones. So that's perfect. Okay. So now we're actually going to write the program to do this. Okay. So let me come in here and I'm going to do, let me do subtraction 2. Okay, so let's do like we did before, and let's imagine that the numbers, the input numbers for this, are going to be in 2 memory cells, let's say FD and FE. Okay, so let's load those into memory, and so we're going to take FD and subtract whatever's in FE from it. That's our goal. Okay. So the first step is let's just loading those two numbers. So what do I need to do to load in FD into a register? What am I going to type? Oh, sorry. Yeah, okay. Let's do the assembly first and then we'll machine codify it. Yeah, good point. So what is it in assembly? Not store. Load. Load register. Which one? With where? Where? FD. Okay, so let's look at the syntax of that. There are 3 pieces, or several pieces there, right? The mnemonic, which is the actual instruction, and then the specifics to that instruction. So those are called operands. So in this case, I want to take data from a memory address, move it into a register. So I need to specify, well, which register and which memory address. Okay. Similarly, what do we want to do for the other number? Yeah. So let's just put the other number in register 2. Fine. Okay. We also know that we need to have the bit pattern of all ones so that we can do the flippy stuff with it. And we also need the number 1 so that we can add. Okay, so we need to get those 2 things into register so that we have them to work with. Okay, so let's get register 3, say with the number 1, and register 4 with the bit pattern of all ones, which is what in hex, pray tell, in hex, not decimal. FF, that's 255. 256 would require a 9th bit, okay, which we don't have. So, okay, so it's FF is the bit pattern of all ones. Yeah, good. Okay, so quick question. What's the difference between the hashtags and the dollar signs? Right, the number is a number, that specific number. The dollar sign is referring to a mailbox. So not the specific number FD, but the mailbox whose address is FD. Okay, make sense? Okay, so we've got all 4 numbers loaded, okay, that we need to process. The 2 input numbers, and these are the 2 auxiliary pieces, that's all ones, and the number 1, okay? Okay, so the next thing I need to do is to flip the bits part. Okay, so I need to flip the bits of what is currently in register 2. So I need to exclusively OR registers 2 and 4, and I need to put that answer someplace. So where seems like a good spot? How about register 5? Okay, so XOR, register 5 is the destination, and register 2 and 4 are the sources. Okay, and in fact, let me put some spacing here just to make it a little bit easier to read. Okay, okay, is that okay? So we're going to exclusively OR those 2-bit patterns and stick the answer someplace about register 5. For the most part, it doesn't matter what registers you put things in, right? I mean, don't be random about it. You know, just be logical. With one exception, and we'll start to talk about this towards the later part of the class. Is register 0 has a special purpose, and so my advice is, unless you're going to use it for the special purpose, don't touch it. It'll save you a lot of headache. Okay, so got that. And so now register 5 has the, hang on one second, has the flipped bit pattern. Yeah, Curtis. It overrides it. Yeah. So if, for example, and actually we'll see that in just a second. So if let's say that I have changed all of these LDRs to R1, then uh, it would load in, this would overwrite, this would overwrite, this would overwrite, and in the end it would have, say, FF in it. Okay? And that bears mentioning because for a very complicated program, if you only have 16 registers, okay, really only 15 because register 0 is sort of special, um, that sounds like a lot, but it's not. Okay? And so you have to start reusing them for multiple purposes. And that's where it can get confusing if you don't think. Yeah. Uh, Depends on if it's before or after. Yeah, so if we did something to register 2 after the exclusive OR, it won't affect what's in register 5, right? Because that was computed from earlier, right? So when in time these things are computed matters. Now, where you have to be a little careful with what I just said is this also, what I just said assumes there's no loops in the program, right? Because if you loop and you go back up to something, then yes, it could be different, right? But we haven't done the loops yet, so we'll get to that. Okay. Let me give you an example of where overwriting is actually useful. So if register 5 currently has the flipped version, what do I need to do? What else do I need to do to that? I need to add 1. Okay, so let me add 1 to the flipped version. So I would do this, right? And I'm going to add register 5 together with register 3. And where am I going to put that answer? I could put it in register 6, but I'm going to put it back into register 5. Okay, and the reason here, it doesn't actually matter, right? I could do register 6, that's perfectly fine. But the reason I'm in this case going to just reuse register 5 is once I've got the flipped version and I add 1 to it, do I still need the flipped version anymore? No, I no longer need that number. It was sort of an intermediary to getting to the flipped version with 1 added. So I can just recycle the register. Okay. Okay, so now what's in register 5 is the flipped version added 1. Okay, so register 5, after that addition is computed, contains the negative of whatever was in register 2, the second number. Okay, and so what do I need to do with registers 1 and 5 now? I need to add them, and here I will put the answer in register 6. Because I might, in this program I don't, but in a larger program I might still need to keep a copy of that negative number around someplace for future use. Okay, so all those lines collectively together, we'll do subtraction. Okay, then to polish this off, we need to stick the answer someplace. So what would be a good thing? Let's put it out in memory, and let's put it at memory address FF. Seems like as good a place as any. Yeah. And then finally, we can roll. Nothing left to do. Okay. All right. So questions about the logic, the flow, why we had to do things this way? Yes. Uh, Registers are inside the CPU. They're like little memory addresses, but there's only 16 of them. Memory is external to the processor, and on our system, there are 256 memory addresses. Okay, on a real computer, like well, even like let's take back in the day, my Commodore, um, the Commodore, the registers in the processor. There's basically three of them, and but in memory you have 64 kilobytes of it, right? So there's always way more memory than there are registers, and exactly how many registers there are and what they're called depends on the architecture you're on. So in this one, it's A through, or sorry, 0 through F for the registers. On modern ARM, there's 32 of them, but they have some of them with special names, and yeah, that's yeah, those. Good question. Okay, so why did say, for example, the 6502, right, from the 80s, well, 70s, why did it only have three registers? Why not just give it 300? Well, because if it's on board the processor, then you have to use transistors to build memory, right? So the same way that we use the transistors to build the logic gates, if you combine logic gates together in a clever way, and we'll maybe talk about this a little bit later, you can actually build memory cells, okay? So if you do that, and let's say it takes 50 transistors to build a single bit worth of memory, and now you need to have at least eight of those because that's for one 8-bit register. Well, then it's a problem of numbers, right? So the more registers you want to have, the more transistors you have to pack into your processor, which makes it more expensive to produce. Okay. Um, well, okay. So when you say big computer, what do you mean? Um, so a company-made computer. Okay. Not really, no. Well, for a couple reasons. Okay, so how are processors actually manufactured? So let me show you this. So let me show you a picture. Okay, so here's a good picture of sort of what this looks like. Okay, so processors are made out of silicon, right? They're semiconductors. So we start with a what's called a wafer, okay, which is just a very, very thin plate of silicon. Um, and then you go through a very complicated process of applying film to it, exposing it to certain frequencies of ultraviolet light that react with like a pattern, okay? And what the parts that get exposed to the light, the film that you put on top reacts with it, and the parts that aren't exposed don't. And then if you expose that film to an acid, it'll eat away parts of it, but not others. So you can etch a pattern in the silicon. And then, so the act of doing this is you etch it with a certain pattern, then you fill in the parts that you etched with a new material that's either negatively doped or positively doped, and then you put a new pattern, etch, fill. So it's like this really, I mean, there's hundreds of steps of this, okay? In order to get uh, well, basically to make a bunch of transistors in some sort of pattern, okay? So what you're looking at here on the wafer is these are all identical copies of the same pattern, right? So when you make it, like, think of it this way: if you want to make a bunch of cookies and you want to make a bunch of identical chocolate chip cookies, do you want to just bake one individual cookie at a time? No, of course not. You put the pieces of dough out along a baking sheet, right? And you pop, a dozen worth or something in the oven simultaneously, right? And then they'd all come out, and you'd have, I mean, they're not identical, but you get the idea, right? So you do this, the square area of this, like the side length here is millimeters scale, okay? And but your wafer could be, this big. Um, and so you're going to do lots and lots of these at a time. Okay. So if you want to add registers to your processor, that means more transistors, which means what in terms of these squares? Different patterns, yes, but how big would those squares need to be? They're small, they are. But if you want more transistors, and the size of each transistor is a fixed quantity, then if you add more transistors, your squares have to get bigger, right? Which means you can't put as many of them on a single wafer, which means it costs more per unit because they have more area. It also means, and this is the other key, when you produce a wafer like this, not all of them turn out perfect, right? Some of them turn out defective, and you have to throw them away. So if you go and you make it more complicated, your pattern, the greater the likelihood that there's going to be a fabrication error and you're going to have more defective parts, which again drives up your per unit cost. Okay, so so what's happened over the last 40 years of processor manufacturing is um, packing on more transistors, but also trying to shrink how big each one has to be means that you can pack more of them into the same amount of space, which gives you better processing capability or more registers. Or what uh, uh, more modern processors do is they actually have layers of memory that are inside. They're not called registers, it's called cache, CACHE. And modern processors can have upwards of several megabytes worth of that on it. In fact, uh, at least from a consumer standpoint, the current processor that has the most that I know of for a consumer product is the AMD's 5800X3D, and that's actually a brilliant processor. Um, because what they decided to do is like, I don't want to make the surface area bigger, so what they make it in two layers and stack them on top of each other, right? And go into third dimension, okay? So they have a regular processor and then crap loads more cache sort of stacked on top, and then it's connected somehow. I have no idea how they actually do it. But that is, so why would you want more cache on board your processors? Well, one application that really benefits from that is games. Yeah, and I don't know about you guys, but I like my games to run fast. Yeah. So you can get improved performance in games, for example, if you've got more cache on board the processor. Now you still need a good graphics card and stuff, but you can squeeze squeeze out some extra performance that way. Okay, so that's been a digression into processor manufacturing. But yeah, more registers equals more dollars is effectively it. And even modern processors, so like the processors that are in all of your iPhones, okay, each core has its own set of registers. So like nowadays you buy a processor and it's like a 4 core or 6 core or whatever. Each core is essentially an independent little processor. So on your iPhones, okay, there are, depending on exactly which model it is, anywhere from 4 to 8. And each one of those is going to have 32 integer cores and 32 floating point cores. And that's sort of enough. And then some cache and other things. So, yeah. Okay, so that's crash course in process and manufacturing. So let's get back to programming. Um, but I guess the salient point too is what is less expensive, packing more transistors onto a processor die or memory that's external. The memory that's external is cheaper, and so in some sense, like you really only need, you could get away with having basically only 3 registers or so. It just means you have to use memory a lot more. And so if we only had 3 or 4, we'd have to load something in, do something, stash it back out in memory, load something else in, do something, stash it back. So we'd be reading and writing from memory a lot more. And but memory is cheaper, right? So it's speed versus cost is part of it. Okay. Okay. Good question though. Anything else on the code here before we try this thing out? No, look good. Okay. So in order for us to run this, of course, what do we have to do to each line here? Yeah, we've got to turn it into the machine code, which means going through and knowing the table, right? So we need to do 11FD, 12FE, and I have most of these memorized. 2301, 24FF. XOR is operation, I don't remember. Let me go look real quick. XOR is 9. Okay, so it'll be 9524. Add is 5553. 5615. 36FF. And C000. Okay, um, so how did I do that so quickly? I had it memorized basically, and you guys eventually will just by osmosis. Yeah. Why you need these numbers? Because that's what actually goes into memory. So give me a second and I'll show you. Okay. Um, okay. So, but you guys agree that all I did was basically use the table to produce that set of numbers. Okay. The next thing I'm going to do is just put them all in one big line. And so all I'm doing is copying them for convenience, and you'll see that in just a second. Oops. Okay, so all I did was just take each individual one and just string them all together. Okay, all right. Let me know when I can move to the web, the simulator. Anybody still writing, scribbling? Good. Move to simulator. Speak now or forever hold your peace. Or hand on top of your head when you're ready for me to move on. Yep. Okay, we're all ready. Good. All right. Oh, and you're Liam. He's sitting there. Yeah. Rub your tummy, pat your head, and do hop on one foot while you do it. Yeah, I can't juggle. I can't shuffle cards, but I can do that. I can't bridge shuffle. My hands just don't do it. Yeah. The other thing I can't do, so like cigarette lighters, I just can't do that motion. It just doesn't. My hand just will not do that. Well, yes, you just roll your, but no, I can't do it. Okay. And so, I mean, I also don't smoke, but if I want to light a candle or something, I use like a barbecue lighter. So imagine if I did smoke and I'm pulling out a cigarette and then, freaking barbecue lighter, right? Um, yeah. Uh, okay. So, where I want to go is over to our simulator. Okay. And in the URL after the hash mark, I'm going to paste in that sequence of instructions, hit enter, and then refresh the page. Okay, so then, and this will hopefully answer your question, what do you see in memory? That's our code, right? 11FD, 12FE, 2301, 24FF, blah, 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 blah. Okay, so uh, Joel's emulator here is set up where if you put that string into the URL and hit enter and then refresh the page, then it will just load all that stuff in for you into the appropriate memory cells. That's very nice because otherwise you have to go and click each individual memory cell and type in 1 byte and do it all the way. Do you want to do that? No. Okay, so this is just a more convenient way of loading in your programs. The other thing it means is how do you turn in a program to me? Well, in addition to typing out the assembly, which is what we did in the other window, you're also going to give me this link. And then if I want to run your code, all I have to do is click it. It takes me to Joel's page with your code loaded, and I just have to hit the run button, and I can see what happens when your code runs. Because do I want to sit down and type out all 46 of your freaking code into this website? Yes, I really, really want to do that. I do. Okay, because I have nothing better to do with my life. Okay, we do need to make one other change though to the memory, which is we need to pick two numbers to work with, right? What numbers do you guys want to subtract? 16 and 23. Okay, what is 16 in hex and what is 23 in hex? Mm, in hex, not binary. 16 is 1 0. What's 23? Mm-hmm. It's 1 7. Okay, and actually, let me put them in the other order for reasons that'll become clear in a moment. But I will switch them later because the result could be a negative number, right? If I do 17 or 16 minus 23, right, I'm going to get -7. If I do 23 minus 16, I ought to get 7. But let's start with the positive answer, okay? So here's the other thing that's nice about Joel's emulator. 7 hex is 23, right? Yeah. If you hover over it, look what happens in the inspector window. It shows you the values and the binary too. Okay. One caveat though, the floating point value, ignore it. It's not correct. Okay. And the reason it's not, well, I shouldn't say it's not correct. I think I mentioned this last time. Brookshire, in his book, when he did the floating point stuff, did not do the hidden one, and we did in order to be compliant with IEEE 754, right? And so this decoding is assuming the not hidden one. Okay, whereas we had the hidden one. So it's not wrong, it's just it's decoding and encoding using a different floating point standard than the one we talked about. Okay. And it wasn't until actually IEEE 754 that there was a standard for floating point encodings. And this actually came up in the earlier class. The uh, Brookshire's book is on the 13th edition. I don't know when the first edition was published. I need to actually go look and find out. And the reason I'm curious about that is because IEEE 754 was from like 1984, 1985, somewhere in there. And so it's not outside the realm of possibility that the first edition actually predated that. Yeah, so I don't know. Yes. So if this was made in 2013, why did you use that? Because the book doesn't. Even the current edition of the book doesn't. So now that begs the question, why does the current edition not make it compliant with IEEE 754? Well, because the hidden, yes, because it was written for Danny's. No, because you guys remember when I first started explaining the hidden one, you guys were like, whoa, 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 this is silly, right? But eventually you guys caught on and it made sense. Well, if I didn't have to explain it, that makes it easier to explain the whole process, right? So that's why I think he did it, is just to simplify that part of the book a little bit. Because, Danny's need to learn computer science too. Yeah. Okay, so let's run it and make sure it works. Et voila. What did we get? 7. Brilliant. Yeah, it worked. That's pretty cool. Yeah? All right. Well, let's change the numbers around, right? So this is the benefit, of course, of loading the two numbers in from memory, is that you can change them to be to whatever you want. Well, what would happen if I subtracted in the other order? Then I should get -7, correct? And what did we get? F9. Well, what does F9 represent? It ought to represent -7, okay? And does it? Well, two ways we can check. We can hover over, and sure enough, okay, but if we wrote out the binary, right, we know that that's a negative number, so how do we figure out its value? Well, what about if we flipped its bits and added 1? We would get the bit pattern for 7, right? And so that would mean that this bit pattern is for -7. Okay, but we've done that before, right? You guys know how to do it. But the inspector is just there to kind of speed up this process for us. Okay, there we go. Works. Question, preguntas, fragen. 9? Yes, sir.
So in the 0, 0 column,
Mm-hmm.
you said that was a special one, right? Or is it the one on the left special?
Yes. Okay. The registers. So see where it says GPR? That stands for General Purpose Registers. So it's register 0 that has a special purpose. Memory cell 00 is not special, except that that's where your first instruction starts, right? So when you run this thing, the program counter's value starts at 0, 0, and the instruction register is, well, whatever, right? And so actually the program counter and the instruction register, those are also registers, but they are special purpose as opposed to general purpose, okay? So hence the name. Um, so yeah, so when I said earlier, like, a modern ARM processor has 32, well, that's 32 general registers, and then it has the specialized ones like um, uh, the program counter, the instruction register, a flags register, some status registers. It's got some other stuff, but basically 30-ish that you get to work with, roughly speaking. Okay, does that make sense? Yeah. Okay, so there we go. We can do subtraction. We can do addition. We can do subtraction. And if we can do those two things, we should be able to therefore do multiplication and division, because multiplication and division are just repeated or are built out of addition and subtraction, right? So we can do all the math that we could possibly desire with this thing. Well, integer math, we're not floating point. So speaking of math, and this is where we're going to do start talking about actually using it as a computer instead of what we have done now, which is it's a glorified calculator. Okay, so it's sort of a glorified programmable calculator. Not all that exciting. What makes a computer is the ability to make decisions, right? So having things like an if-then construction and being able to decide what instructions to execute based on some condition, okay? All right, so in order to sort of motivate this, how could we decide, hey, Eric, how could we decide if a number is negative?
That's a good question.
Okay. In binary, how can we tell if a number is represents a negative? Yeah, if the far left bit, okay, which I'll call the most significant bit, if that is a 1, we have a negative. And if it's a 0, what do we have? Well, not necessarily positive because you could have 0. So it's non-negative. So it either is negative or it isn't. Okay. Yes? Okay, yeah, 0 is kind of the monkey wrench here. But is 0 really that bad, excuse me, to worry about? No. Okay, so I am interested in looking at the far left bit of a number to determine if it is a negative or a positive. Okay. Similarly, what would happen if we looked at the far right hand bit instead? What does that tell me? Exactly. It tells me if the number is odd or even. Okay, now think about why. What are the place values?
1, 2, 4, 8.
Right? And so all the place values are even numbers except the ones place, right? And if you add together a bunch of even numbers, what kind of number do you still get? An even number. So the far right-hand bit, the ones place, has unilateral control over whether or not the number is odd or even. Okay, we call that parity, by the way. Parity is its oddness or evenness. Okay, and for that matter, we do include 0 as an even number. Okay, good. All right, so let's take the negative positive thing. We need to examine the far left bit of a number, but we have the whole number. So we can't just, and then there's no instruction in that table that says, look at this bit, right? So how are we going to build the ability to strip out a bit that we care about and not have a bit that we do, or bits that we don't care about? We're going to do a trick that's kind of like what we did with the subtraction. Okay, so let me come back over to here and let me start a new file, and I'll call this detect negatives 2. Okay, so the idea is let's take a number, a binary number, and what was it that we had from before? It was F9. I'll just use that as my running example. So that's F, and then 9 is this. Okay, and I'm going to put some spaces here for reasons that'll become clear in a minute. And I'm going to use this number for something. Okay, 1 followed by all zeros. And I'll explain why I chose that number. So with the flipping the bits trick, we needed two things. We needed a cleverly chosen number and a cleverly chosen logical operation. So in that case, we chose the number, all ones, and the operation, XOR, and it did the job. Okay. Here, we need a different number and a different logical operation. I claim that the number we need is 1 followed by all zeros. Okay, and the reason that I want that number is because, well, which bit do I care about? The far left one. So I'm going to put a 1 in the position of bit or bits that I care about and a 0 in all other positions. But now I have to choose the logical operation. Which one do I want to pick? Well, we got, what are our choices for our logical or arithmetic operations?
Or
We can do inclusive, exclusive, or. We can do and. We can do addition, and we just figured out how to do subtraction. All right, so which one of those is going to do the job? All right, let me convince you that it's definitely not addition and subtraction. If I do addition and subtraction, the first number could be whatever, right? So how many different answers could I possibly get if I did addition with this specific number? Well, way more than 2, right? I could get, well, presumably 256 different answers. Okay, do I want to get, so let me back up. I want to choose an operation that will give me precisely 2 possible answers, because 2 allows me to make a decision, yes or no. 256 things, no, that's not going to work. Okay, so if I add, then the first number could be whatever. And so if I add, I'm going to get a whole lot of different possible answers. So that's not going to work. Subtraction, same thing. All right, so what does that leave us with? Inclusive or, exclusive or, and. Any thoughts? It's not exclusive or, it's not inclusive or, it's and. And let's think about why. Okay, the reason is, what happens if you and against a 0? What do you get? A 0, no matter what. Okay, if you and against a 0, it doesn't matter what the other bit is, you're going to get 0. But what about if you and against a 1? You get a 1 or a 0 depending on what the first number was. Okay, so the 2 possible answers that we could get when we do this anding are either this, okay, or we get one of those 2 answers. Precisely 2 options. Okay, are you guys convinced that no matter what the first number is, as long as we do and the second number is 1 followed by all zeros, then what I just wrote on line 7 on the screen is correct. We get exactly one of those 2 possible answers. Yes? Okay, that means we have the basis for making a decision, a binary decision. Okay, yes, no. Okay, so the way to think about the decision process, right, is so far our programs have just been a straight line. Okay, so imagine that it's like we're walking a path through the forest, and there's just a path, and we're just walking along the path, and eventually we come to the destination, which, I don't know, maybe there's a magic well or a sword in a stone or something, right? Something cool at the end. Yes? Okay, so is that the only way that we could go on an adventure through the forest? Certainly not, right? Because we might be walking along the path and then we come to a fork and we have to decide, are we going to go to the left or to the right? And if we go to the left, we see one part of the forest. And if we go to the right, we see a different part of the forest. Is it possible that those paths come back together at some point? Sure. Is it possible that one of those paths takes us in a loop and actually takes us back to some place we've been previously? Sure. Right? Do you want to go in circles forever? Probably not. Right? So that's the decision we need to make. Okay. Now let me do one more thing and then we'll quit. Which is to go back to the operation that's going to do the heavy lifting here. Okay, is operation number B. Okay, and the mnemonic for it is BEQ, branch on equals. What it's going to do is compare a register to register 0. And if their contents are the same, then you will branch and take one path. Otherwise, you'll keep going on the path you're currently on. Okay, so now do you guys see why I said don't touch register 0 for most things? Except this. Use register 0 because that's the one that gives you the ability to make binary decisions. Okay, we'll pick up with that and actually code all this stuff on Monday.